Hello and welcome to the third video in the series of how to use Threatray. In this video we will be looking at how Threatray supports typical reverse engineering workflows. If you haven't seen the previous two videos on detection, identification, as well as hunting and pivoting, I really recommend watching them first because it provides a lot of background and basics on the platform itself. In this video we will also continue using Latrodectus as a nice example, trying to figure out what are the differences between the variants that we have discovered in the previous video. You will find links to the previous videos in the descriptions, and let's get started with this one. Good, so for everything related to reverse engineering, Threatray provides an IDEA Pro plugin, which really brings the type of intelligence you have in the platform directly into the disassembler. During the course of this video, we will also see how the plugin helps to differentiate known good from known bad code, how to hunt for single functions, and ultimately how to cluster a set of binaries to identify shared and unique code. So to get started, first up you will need to download and install the IDEA Pro plugin. You can find a link here in the help section, which leads you to our docs, and you will find the link here to the IDEA plugin. So I've already downloaded and installed that, and we will here get started with a Latrodectus sample that we've seen in the past. So this is actually the original sample that was discovered by Walmart back in October, right? 8th of October 2023. And our goal here is to kind of get started with this particular sample here and try to figure out how we can dive a little bit deeper and reverse engineer this particular case, as well as a couple of variants that we've seen in the past. So our goal is really to dive deep into one specific area that Walmart, as well as Proofpoint, who had a big blog post about Latrodectus as well in, I think, April of this year, regarding the string decryption and how it works and how it changed over time. So let's start with this particular sample, the patient zero, so to say, and you can always kind of download this payload here as a zip file. So of course we want to have the actual payload of Latrodectus, and we can also see here in the OSINT hunt that this is actually the binary that was originally mentioned by Walmart in this IDE blog post. So I already downloaded that, unzipped it, loaded it into my IDEA Pro here, and what we can see is essentially a flat binary here without any annotations. And of course one of the main challenges here is now to kind of give semantics or value to these functions by understanding them, and notably also understanding what is known good functionality that I might not need to study, what is known bad functionality, what is unknown. And this is something Threatray can really help with, since we track a lot of known good as well as known bad code. You can kind of transport that intelligence or apply it to IDEA Pro on this level here. This is very similar to what you would have from Flirt signatures, for example, or from Lumina if you're using it, just in a more kind of comprehensive or powerful way. So to do so, you just open the context menu with a right click, press Show Code Detections per Functions, and that will now try to kind of fetch all the intelligence about all of the functions in the binary. Of course, you will need to first have analyzed the binary in Threatray, otherwise you don't get any intelligence here. So what we get here is some advanced options on how to configure these code detections, how to apply them, which to apply, which not to apply. In this case, we just go with the default that is good enough here. So that then does two things. You can see on the left-hand side that now a lot of these functions got renamed and recolored as being benign, being malicious, belonging to Latrodectus here, and being unknown. Secondly, what you get is this list of code detections here on the right-hand side, where we essentially characterize each function or each address to belong to a specific malware family, and we also give the reference malware file, including the matching address in the reference malware file. So the reference malware file is essentially the file that Threatray used to create this code-based detection. And if you would like to verify whether or not this is actually Latrodectus, you can always pivot to this kind of to this analysis of the file and verify that by yourself. That really gives you transparency on how we got to the conclusion that this code belongs to Latrodectus. This is actually the same functionality that you also have in the user interface. And if I switch back over here, if we go again to this Latrodectus payload, you have this button here, show code detections. That will load essentially exactly the same list that we had in the IDEA Pro interface with the addresses, code detections, the reference malware file, which we could pivot to here, but we're not going to investigate that. Okay, good. So next up, we kind of need to find this string decryption routine, and there are many ways to go about that, of course. Helpfully, in the OSINT report from Walmart, they actually hinted towards how this string decryption function looks like. So if we navigate to this report here, then here they start talking about string decryption. They have a XOR loop, which calls a pseudorandom-like function. And we can see that this pseudorandom-like function kind of uses plenty of shift right, shift left operations. So essentially what we're going to try and do is hunt or search for exactly these type of instructions. So this is shift right. That gives us basically two functions here. Yep. And if we look at one of these two, we can see that this basically looks like what we saw beforehand with shift right and shift left. So that's kind of one of the two functions of interest. So we rename that here, BRNG, so we keep track of it. And then the blog post also mentioned that the calling function, which is this XOR loop, is of relevance. So if we go to the caller function here, we can see actually this XOR loop exactly as described. So you've seen beforehand, right? This the PRNG function is identified as Latrodectus, whereas this XOR function is unknown. That's completely all right. We're just not tracking that apparently, and we can rename this as XOR loop. And now we basically have our two functions that we care about labeled. Okay, filter for them. Here we have them, right? So next up, we actually want to know and understand in what other Latrodectus variants that we have in our data set these two functions appear in. And we've seen in the previous video how we can do retrohunting, and the retrohunting we've seen there basically takes all the functions in a binary file, hunts for them, and gives you a list of similar files. Here we can be much more precise. Now we can really just select these two functions and actually hunt for these two functions. Selecting them, right-clicking, function retrohunt, and then we can choose a threshold. So here I can define if, let's say, one or two of those two functions appear in a file, it should report it as a match. So here I'm choosing two because I'm interested in all the variants which actually have this combination of functions. And we can get to searching. That now goes through 100 million plus binaries, billions of functions actually, and gives us back a nice matching list here. And we can see that we have a range of file hashes here appearing from different analyses that have these two function matches. And if I scroll through this list here, we can also see that the malware family that are detected here it's always Latrodectus, right? So with this, I can also now conclude that these two functions appearing together, they must really be unique to Latrodectus. Otherwise, I would have found a lot more, especially different samples. That, of course, is super helpful for understanding that this is unique. However, also to use that as input for detection engineering. So I could use that to create a YAML, because now I know that this code is kind of unique to Latrodectus. And that's a really good use case to kind of verify or vet the uniqueness, or maybe not uniqueness, of particular functions. We can also see, if we sort that by the timestamp of when the analysis was created, that goes from the beginning, so really the 8th of October down here to basically early one at the end of the May, right? So we have quite a broad selection of samples from 8-9 months that kind of match this particular set of functions. Now, we've also seen beforehand that we actually have Latrodectus samples from beyond May, which aren't matched here. So that might lead us to the suspicion that these two functions are not covering the entire set of what we know as Latrodectus. And now what we want to do next is figure out whether or not these two functions actually always appear, or whether or not they changed. So the way we do this is we go back here in our UI, and what we want to do is we want to essentially collect a couple of variants of Latrodectus, which we can then use to cluster them. And by clustering, we can get an understanding just over a small set of samples, which code is shared, which code is unique. And that should then also lead us to understand whether or not these two functions that we're looking at are commonly reused in Latrodectus, or more to a uniquer set of variants of Latrodectus. Okay, so the way to go about this is, there's multiple ways, of course, but what is super helpful here is this OSINT hunt, where I essentially get a list of diverse samples from a large spectrum over these 8-9 months or so. So what I'm doing here is I'm basically trying to pick variations. So I'm not trying to pick 5 times basically the same code, right? I'm trying to pick variations, maybe this one here, maybe this one here, and let's go a bit further, maybe one of these here, right? So I kind of get a diverse set. And here again, I essentially need to have the hashes of this unpacked Latrodectus, which I can pivot to with this location column, just to showcase that in another tab. Here I basically have then another variation of Latrodectus. I get the hash from here, and with that I can collect a set of hashes, which I can then use in the IDEA plugin as input to launch clustering. And I have already done that. I've selected a couple of variants beforehand with exactly this methodology here. And what we can then do is cluster this file that I have open here against a couple of other files. So these are 3 other variants, so that gives me essentially 4 files that I'm now clustering. And what I can do here is then get an impression of which functionality is shared and which functionality is reused. So what we see here is essentially a list of the functions in the binary that I have open here, and whether or not some of them appear in the other 3 binaries. This is sorted by what we call a prevalence score. the higher the prevalence of this particular function here, the more frequently it appears in the other binaries, which in this case here is 4 out of 4, meaning that this particular function is, let's say, stable over this set of 4 binaries. And if we scroll down here, there's also a couple of other functions which are not as stable. They only appear, in this case, in 2 out of the 4 functions. So now, naturally, what we're interested in is whether our annotated functions, these malware functions that we found beforehand, appear in all of the 4 samples or just a subset of those 4. So we can filter down here, and we can see that this XOR loop and PRNG function, they only appear in 2 out of the 4 samples. And actually they only appear in, of course, the sample I've opened right now, as well as this 947 sample, right? So that already gives me a clue that these 2 functions don't seem to be reused over all the variants of Latrodectus, and that is actually something that was also confirmed by Proofpoint. So apparently Latrodectus started changing how they do string decryption in, I believe, early March of 2024, and that kind of confirms what we saw there. We can actually go and check that out. So if I go back here, I think one of those blog posts are from Proofpoint. Let me find the right one here. Yeah, this one here. So this is from early April. And if we scroll to the right place here, yeah. So they kind of noted that Latrodectus started changing how they do string decryption, apparently a downgrade on how it was done beforehand. So that kind of confirms what we have found here as well, right? So now we want to go a step further and kind of understand how this new string decryption routine looks like. And in this case here, now we know how the old one looks like, and now we need to kind of find how the new one looks like. And again, going back to our disassembler here, the way we could approach this is the following. So beforehand we had this kind of list of hashes that we used for clustering here. And if you remembered a match, we had a match on this 9470, but these 2 ones were missing, the 481, 8CA1. So what we now are going to do is, because we know that this 481 does not include these 2 particular functions, is we basically just take this particular hash. I've downloaded that from the platform, opened that, which is this 481, and now what I'm going to do is I'm kind of turning it around, and I'm clustering this particular case against our patient 0 that we had beforehand. So I'm clustering this one against what I had beforehand, which is this one here. So that's our patient 0 hash. I cluster against that, which then gives me here again a set of functions that are shared between those 2. And of course, what I'm now looking for is which functions are not shared. So if I go through these functions here, which only appear in one of those 2 files, then pretty quickly I'm going to find the actual function which is responsible for the XOR loop. That loop still exists. Looks like this. You have the same loop here. You even have a call here to this pseudorandom function, which is, as Proofpoint reported as well, basically just a very simple increment function. So that then leads us to this particular XOR function, which is now used in this variation of Latrodectus. And a nice way to kind of go further is to then also retrohunt for this particular function. So I'm just retrohunting for that. which then will also give us a nice list of variants which are using this particular string decryption routine. And if we look at that, we can see that we have some more recent variants from June that we didn't have beforehand with the old one, and we can probably narrow that down to first appearance somewhere in February of 2024, where we had the first appearances. But it doesn't go further back, doesn't go to our patient 0 back to 2023. So this is a really nice way to now kind of separate between the older variant with the, I guess, more complex string decryption routine, as well as this newer variant which has replaced this string decryption routine. All right, good. So this kind of wraps up the video, and now we were able to kind of dive very deep into some of the details of Latrodectus with the help of Threatray's IDEA plugin to kind of characterize functionality, hunt for specific functions, cluster, understand similarities and differences, and yeah, it's really smooth integration of intelligence into reverse engineer's workflow. So thank you for watching, and see you in the next one.